Suppose unit amount of force displaces a ball by unit length, and as we have applied it along x-axis here, the ball is displaced horizontally by unit length. In this system, if some force along any arbitrary direction displaces the ball from origin to a point V, then the displacement of that ball along x-axis because of that particular force will be the length of projection of the vector V along x-axis, which is interestingly equal to the amount of displacement of the ball by the component of that force along x-axis. Here the distance of the vector V from origin is norm V, and if theta be the angle between x-axis and the vector V, then the projection of vector V along x-axis is norm V cos theta, which equals to norm I times norm V cos theta. On top of that, we can simply check the component of the force responsible for displacement from origin to V will displace the ball along x-axis by distance norm I times norm V cos theta, where along x-axis unit amount of force displaces the ball by distance norm I. So when we have considered the ball to be displaced by unit amount of force along x-axis by unit length, then the force which can displace the ball from origin to the vector V, component of that force along x-axis, displaces the ball by length equal to the length of projection of vector V along x-axis. Now instead of considering unit amount of force along x-axis to displace the ball by unit length, if we consider it to displace by twice of that unit length, then the component of the force which displaces the ball from origin to vector V will displace it along x-axis by twice as that of the previous displacement, which further equals to norm 2I times norm V cos theta. Here norm I represents the norm of unit vector, that is unit length, and changing the length of displacement by twice here is equivalent to scaling the x-axis by twice. So simply if we consider the length of unit vector along x-axis to be twice as that of the previous unit length, then that will coincide with the point representing vector 2, 0. With respect to this transformed coordinate system, we get our new transformed vector V, whose projection over x-axis is twice as that of the previous one, and the projection exactly coincides with the center of the displaced ball, which was displaced under the condition that the unit amount of force displaces the ball along x-axis by length twice as that of the length of previous unit vector. Here you can realize that the geometric interpretation of that particular condition is analog with the transformation of the coordinate system by scaling it along the constraint vector accordingly. Now here, we have seen the projection of a vector V on the unit vector along x-axis is determined by the norms of those two vectors and the angle between them. Therefore, if we have two vectors and the angle between them, then we can find out the length of the projection of one vector along another. And since the angle between two vectors can be determined exactly by those two vectors, therefore we can define a relation between those two vectors which gives a scalar output. Here is the length of the projection, and we call it an inner product or scalar product between those two vectors. and we can represent it by these angle brackets or chevrons, which basically is a function from B cross V to the set of all real numbers, the scalar field R, and is defined by inner product of U and V is norm U times norm V cos theta, where theta is the angle between U and V. Now for this case, if in particular we consider the vector I to be the unit vector along x-axis, then we will get the relation as inner product of the unit vector and V is norm I times norm V cos theta. Now since the function, that is the inner product, spatially doesn't have any such interest on these two particular vectors, rather the magnitude or norm of those two vectors and the fixed angle between them completely determines the result. Therefore, we can consider any pair of vectors having norms and angle between them to be same as these two vectors, and then also we'll have the same result in form of length of projection of one vector along another. Here you know all the different positions of these 2 points represent different vectors in R2. Now let us try to find out the nature of cosines in real domain. Here the variable on the x-axis is theta, and the graph of cosine gives the value corresponding to every single theta. Now from graph of cosine, it's obvious that cosine gives exactly the same value at theta and minus theta, and we can check it. That is, the portion of the curve on the left side of y-axis is nothing but a symmetric reflection of right portion of the curve about y-axis. And this result in particular gives us a way to think about the symmetricity of the inner product. And therefore, we can write down norm I times norm V cos theta is equal to norm I times norm V cos minus theta. That's why we just can flip the vector V to make the angle between I and V equals to minus theta. And here, the length of projection of vector V on the unit vector along x-axis is not changed. Now since the product of two scalars can commute, therefore the expression further represents the inner product of V and I, which is the projection of the unit vector along the vector V. And we can simply visualize it just by applying a rotation on the whole system consisting of those two vectors without changing their norms and the angle between them, and then scaling the unit vector along x-axis as it coincides with the vector V. Now here on this system, you can check that the length of projection of the vector I along V is equal to the length of projection of V along I, that is the inner product of vectors I and V. And therefore, we can conclude the inner product is symmetry. And obviously, cosine plays a crucial role here. So we can visualize the length of projection is unaltered even if we alter the roles of two vectors and scale the coordinate system accordingly. Now if we add the inner product of I and V with itself, then it will be 2 times the inner product of I and V. That is 2 times norm I times norm V cos theta. And we know that is exactly norm 2I times norm V cos theta. On top of that, the formulation gives it as an inner product of 2i and v, and we simply can visualize that. And that's how 2 times the inner product of I and v is equal to the inner product of 2i and v. Now since any vector on x-axis can be expressed as a scalar times the unit vector along x-axis, therefore, further generalization of this result gives that lambda times the inner product of I and v is equal to the inner product of lambda I and v for all lambda in the scalar field. Now, if we consider lambda to be sum of two scalars, lambda 1 and lambda 2, then this equation becomes lambda 1 plus lambda 2 times the inner product of I and v is equal to the inner product of lambda 1 plus lambda 2i and v. And further simplification gives us this result. And we can check the result for different lambda 1 and lambda 2. And the result holds for all lambda 1 and lambda 2 in the scalar field R. Now shifting the scalars on the left hand side of the equation inside the bracket, as previous we get this equation. Again we know that all the vectors on the x-axis can be expressed as some scalar times of the unit vector along x-axis. That is, for any arbitrary vector u along x-axis, we have u is mu times I for some mu in the scalar field R. And that's why we can write down the equation as the inner product of u1 and v plus the inner product of u2 and v is equal to the inner product of u1 plus u2 and v. And further generalization gives us summation of inner products of lambda 1 times u1 and v and lambda 2 times u2 and v is equal to the inner product of lambda 1 times u1 plus lambda 2 times u2 and v for all lambda 1 and lambda 2 in the scalar field R. And this result further indicates that the inner product is linear on its first component. And since the inner product is symmetric, therefore it is linear on its second component also. And that's why the inner product is bilinear. Now if we consider the inner product of the vector v with itself, then we will have the inner product of v and v is norm v times norm v cos 0. Now as cosine at 0 is 1, therefore the inner product of v with itself is norm v times norm v, that is norm v and its square, and here which is non-negative. And that's how we got the relation between the inner product and the norm of a vector. On top of that, equality holds if and only if norm v is equal to 0. And in other words, we can say v is a zero vector. And therefore, we can conclude the inner product is positive definite. So long story short, we can define a bilinear form on a vector space, where a bilinear form is a real valued function of two vector variables. So here the inner product is a bilinear form, and a real vector space together with a symmetric positive definite and bilinear form is called an Euclidean space. However, the inner product is much more general and can be extended to other non-Euclidean spaces. And lastly, here in this lecture, we have got a relation between the norm and the inner product, where the norm is also can be determined by Pythagoras theorem. So it's quite natural to think how we can relate the inner product with the Pythagoras theorem, and so on.